So let's go back to vertex cover and let's try to understand them in terms of the language we established just now. Okay? You want to delete k vertices to kill all edges. This is your goal. For example, here, this is a vertex cover, right? Look at every edge. There is one orange guy. Yes. Simple, simple. This is very simple. This is not very hard, if you follow. So what do we think? So we can think edges as two uniform family over the ground set V. Agreed? No?
Yeah.
Right? It's like, so let's make, I mean, it's all about making a family, right? Let's rub this. Okay? No? Otherwise you may not like me for. So what is our universe? And what is our family? U comma V. U comma V is the edge of my graph. This is it, right? So I think of edges as a two uniform size family over a ground set V. Okay? Now, and what is our goal? We want to make a kernel. Means we want to find a small subset of edges such that G, look at the graph induced on these edges. It is a yes instance if and only if G is a yes instance. We have done a kernel in the morning by high degree rule and blah, blah, blah. So let's do a slightly non-trivial kernel with the same bounds. It's just it's a nice application. Okay? And we want to use whatever we did just now.
Well, I mean, in general, well, the graph on the left should not be also from G of X, right? But in this particular case,
yeah, in this particular case, generally it's not true. Okay? So all I'm trying to tell you that look, I think of the vertex cover problem. I want to think of a vertex cover problem. Here I have UV, blah, blah, blah. And I want to do one rep set computation and I'm done. Okay, here's my kernel for you. Okay? We'll prove it in a minute why, but just to intrigute your, let's compute f hat of f. K representative. What is its size? What is the size of f hat? Question number 1, size of f hat. Question number 2, how much time does it take?
well, the time is written here, we just need to remember.
I said compute K representative for these guys. So if you remember, the size was, no, it's K plus 2 choose 2 because size of the family plus the representative. So if the size of the family is P and future is Q, which is like K, so P plus Q, choose P. This is what it is. So in our case, P is 2 and Q is, because I wrote K, it is K. So it's K plus 2 choose 2. And how much time it will take?
To the K.
Is it going to take 2 to the power K? Or did I do something wrong here? P power Q or? No, it should not be taking this much. be branched in p ways p power q, right?
Right.
Okay. So this algorithm is not good enough. This does not run in polynomial.
You mean 2 to the k is too bad?
Yeah, if I'm making a kernel, it's bad. It's not polynomial time.
Right.
It's not polynomial time.
Right.
Because all I gave you is an algorithm with running time p power q. Very bad. Okay. So there is also an algorithm. Okay, so there is this algorithm. There is also an algorithm by Daniel Marks, which actually does in k power, I think p plus q to the power p into t. There is also an algorithm like this, okay, to compute these rep sets. Now, if you'd have applied this, then it will be k square time. So, if you'd have applied this algorithm, it will be k square time m, so like some big O of k square time m. And if you apply this algorithm, p is 2, q is k time m square, right? Okay. So let's apply Daniel's algorithm. We will also know one algorithm, don't worry, in a minute. Okay. But suppose I found this and I tell you, over, this is your edge set. Is it correct? No? Okay, guys. If G is a yes instance, then G of x is yes instance for any subset x subset of E, right? If I have a k size vertex cover, right? So what do I return you? I say, look at your f hat. Look at your f hat. Look at the graph induced on the vertex set of f hat. What is the size of this? Is basically 2 into k plus 2 choose 2, which is like roughly like order k square, right? Now I'm trying to tell you that this is a kernel. G has a vertex cover of size k. What I want to prove? G has a vertex cover of size k if and only if this has a vertex cover of size k. If G has a vertex cover of size k, clearly this has a vertex cover of size k because it is small induced graph. What is not obvious is this. Why? No? This is not obvious. I mean, I went and computed some representative and blah, 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 and suddenly it should imply that, I mean, why it's true? Okay, guys, it's not very hard. Okay, so what is a no instance? What is a no instance? It means if G is no instance, for any subset S of size at most k, there is an edge that is disjoint from S. That is the definition of vertex cover, right? If something is not vertex, like if it is a no instance for any vertex cover of size k, there is some edge which it does not intersect. Agreed? Okay. Does it rings a bell to you? So what I was computing this, why I was computing this k representative, I said, okay, boss. So I was trying to say that, look at your solution, which is x. If it is no, means for any one, I have some on disjoint. This is all that I'm trying to keep, right? So let's prove it formally. I mean, this is all that it is. There's no magic happening. Okay? Okay. Okay, this I already told you. Let us show that if g of x is a yes instance, then so is z. This time by contradiction. So let's try the solution for gx on g. Okay? So I'm trying to show the reverse direction. Suppose we start with a vertex cover of size at most k for graph induced on x. Let's see why it is not a vertex cover for g. Why it is not a vertex cover of g? Why it is not a vertex cover for g? Well, because some edge is uncovered. Right? Some edge is uncovered. Since x is a k representative family, for any S subset of V, where mod S is less than equal to K. So what does it mean? That look, what did I compute? Look at your F. We said, look at your solution, this edge is disjoint from your solution. So look at this red edge. This edge is disjoint from your solution. It means look at your family. In F, I have your solution. There is some edge which is disjoint, right? Then what does it mean? There is some edge in F hat is also disjoint from your solution. Then why it is a vertex cover of F hat? Look, it's very simple. This edge is not hit by your vertex cover, right? So now look at your vertex cover and look at your family. That as an endpoint, it exists here. Your vertex cover is S. Your vertex cover you gave me, which it is not hitting. I remember, I have to use dark color, sorry. Okay, S. Why it is not a vertex cover of this? Because there is some edge which it does not hit. Okay, suppose it does not hit UB. Now UB is here and its intersection with S is empty. Implies there is some U prime, V prime in F hat whose intersection S is also empty. But you said that S is a vertex cover of this. It's not possible. So you see, you can apply non-trivial algorithm also to compute these kernels. Yeah, this is the most obvious application I have shown you. This is not in either way it's a representative of how you can use this representative. Okay, this is it. Alright, so picturesque, this is what it means. If there's a set E in E such that E intersection S equal to phi, imply there's a set E hat in X so that E hat intersection S is phi. Note that the green edges denote graph induced on X. So it will just mean that your smaller graph is also, this is not a vertex cover of the smaller graph also. This is it. Yeah, you go through each edge and you made a contradiction. This is it. No? Was this also more difficult than previous one? No? Is it easy? We said a very simple thing. We said, look, I mean, isn't it counterintuitive that somehow we are able to preserve all no instances? What are these edges telling me? Look, this is very, like if you think now, so what are these edges? Tell me, look at any vertex cover of size k. If someone is disjoint, some edge is disjoint, then I'm able to keep someone who is disjoint from him. So if someone is no instance, my smaller instance is also a no instance. We are able to preserve a no instance in a much, much smaller way. For any set, I mean, there are some n-choose k sets, right? Imagine a no instance. What it means, if I have a n-choose k sets, because if it is a no instance, any n-choose k sets is not going to intersect all the edges. Now, for all the n-choose k sets, I'm only able to keep k square edges such that you give me this, there's someone who is disjoint from him. I mean, this is what it tells me, is that think that for any, if my graph does not have a vertex cover of size k, it means for any set of size k, I have some edge which is disjoint. And how many sets, such sets I have? N choose k. But for them, I'm only keeping k square edges. And that's the beauty of the theorem. It is able to preserve all no instances in a very small set of objects.
A question. This value, p plus q to the p, there is an algorithm with this random bank for abstract problem of finally represented sets.
Yes. Yes. So that is why otherwise this will not run in polynomial time, right? My algorithm will not run in polynomial time because q is k. So p is 2. So this will be, and the algorithm of Daniel Marks runs in time p plus q choose p times t. That will allow us to do so. Okay, guys. I gave you. Okay. Now, how many of you are really interested in knowing a faster algorithm to compute these representative sets? Because after this, it is like I can give you more application, but they are more involved. But I could also give you a faster algorithm to compute these representative families, which is slightly non-trivial, but not very. If I use the word exterior algebra, blah, blah, in low-verse language, it becomes hard. But if I use just determinant, it should be easy. So I leave it on to you. I have lots of energy to tell, don't worry about me. But it's a good time to just know that, okay, I mean, if I'm not interested, it's a good time to take break.
Maybe what is Matroid?
What? Exactly. What is Matroid? This is a very good question. What is Matroid then? Forget about Matroid, okay? I will not tell you what Matroids are, but I will still use them like very. The point is I do not want to spend my 1 hour giving you basics of Matroids. That was my whole objective. But if I give you an algorithm for this, I will still not tell you what Matroids are, but we are using Matroids implicitly, and I was planning to, at the end, tell you what more things can you do with this if you think of many of these things in the setting of Matroid. That was my goal. Okay. So now, okay, so let me tell you. So do you know what Matroids are?
I don't.
You don't. This is the whole thing. Okay? Okay, forget this.
Maybe everyone else does?
No. We don't need Matroids. Why Matroids? Forget it. Forget them. They are not useful object for our purpose. Okay, guys. Now you ask for the proof, then you get the proof. Okay? It's cool maths though. It's a cool maths. Whatever we'll do is not computer science anymore. It's just maths. Okay? You have to just compute Gaussian elimination and compute some basis and all, but it's just, after this, it is just maths. Okay, let me tell you what did Lova's prove, okay? Okay. Matroid is to sell papers. I have a matrix M, okay? I have a matrix M of size n cross n, okay? Now, and I have a family F. I'll tell you what these families are. The property is that what is the family? Basically, think of this way that 1 to n columns are, and each SI is a subset of 1 to n. They are represented. And what is the size of each SI? Is equal to P. So basically, these SI are some P-size columns. And what more? Now we need more. Says, and SIs are linearly independent. So you are given a matrix over some field F, and all I'm saying that I have been given a matrix, and what is the proper?
SIs are linearly what?
Linearly independent columns.
Okay.
Like, is this okay? Yeah. Okay, very nice. Now let me define a notion of what is a Q representative for this. Okay, and then I will tell you what I want to do. Okay, so now I'm going to call f hat subset of f is a Q representative if the following thing happens. If let x be subset of 1 to m, right? Again, some set of call. Let x be. If there exists some s in f, such that s intersection x is empty, means look at the columns they represent, they do not intersect. Okay, so for example, this is my s and this is my x. Let's think of this way. Okay, such that s intersection x is empty, and look at the columns of s union x are linearly dependent. Okay, what I'm saying?
Can you please repeat? And what?
And look at the union of s union x as the columns. They are linearly independent.
So adding another column and
so look, I have s and I have x. So I said you come up with X such that I have some S in my family so that they are disjoint columns, and look at the union of these columns. This is linearly independent. Okay? So now in the before I only demanded that their intersection is empty, but now I am demanding that in this matrix they should be linearly independent. Okay? Then there exists S prime in my F hat such that S prime intersection X is empty set and columns of S prime union X are linearly independent. Right? So basically if you have S union X which is linearly independent, then I do have some other set. See, it is more. Then what it says that, okay, maybe then I will find you some other S prime so that this union X is also linearly independent of this. Now my question to you is, first of all, what should be the size of this F hat? Doesn't it sound more? I mean, before what we were talking about was sets and families. Here we are talking about, so we can think of each SI as a subspace. We can think of each SI as subspace, right? So each SI and X are subspace. And what it means, S intersection X is phi as a subspace. They are as a subspace, like as sets they do not intersect, and as a subspace their dimension, if I have a dimension of this SI is P, someone has dimension Q, their union has dimension P plus Q. Right? So whatever we were talking about sets, now we are talking about subspaces. So if you do not want to think in those languages, this is all that it means in the terms of matrices. Right? So whatever things we proved for set family, I want to prove for this. I will tell you why whatever we were doing can be thought of this in a minute. Okay? And the great theorem by Lovász is, this is not Bolavas, it is proved by Lovász in 1977, which uses some very advanced algebra, is that this.
What is R?
There is no R. Where you see R?
P plus Q.
Choose P. It's exactly the same bound as whatever we have seen for sets.
And what is Q?
Q is talking about Q representative. So size of future. Think of size of future is Q. So let X be subset of M. You're right. And mod X equal to Q. Sorry. Otherwise this doesn't make sense. So we are only making things for this. So basically, if
What means T?
where?
T. So it's like F is.
Some S1 to ST. This is some family you gave me.
So it's subset of columns.
Each SI is a subset of columns.
Oh.
Subspace in other words.
Okay.
So basically this is, you can think there are subspaces.
S9 is not a column, it's a subset of columns. Okay.
SI is some subset of columns of size P. M could be much larger, right? So P. So basically, think of these are subspaces of dimension P. Okay? Future is a subspace of dimension Q. Their union has dimension P plus Q. This is all that it is, right? So basically, if you had a linear algebra vector spaces, then you can, remember we proved in the morning, AI, BI, right, as a sets. If you think of them as subspaces, this is what this theorem tells. Okay? And this is what P plus Q choose P is. Okay? Now you see matroids? Not yet?
I don't know what it is.
This is what matroids are.
What is this?
These are matroids.
What?
This is what matroids are.
What is this?
What do you call? So think of this with, okay? What is my matroids are? Okay, so look at a family where each of size, say at most P. Family of size all at most P, which forms linear, which are linearly independent. All subspaces of dimension at most P, they form a matroid. This kind of families are called matroids, essentially.
Okay, so my matroid is specially constructed family of subspaces.
Subspaces.
Okay.
And these are called, they have a special name, they are called representable matroids. Okay? So matroids are much more abstract objects, but the matroids, which are basically all subspaces of particular dimension of some vector space, they are called representable matroids. This is it. So all subspaces of particular dimension of some vector spaces, these are matroids of certain kind, and this is what is called representable matroids. Okay, I could also give you some like tedious definition, but this is in my head is much more nicer to keep it. They are basically all subspaces of particular dimension in some vector spaces. Okay, because you are a mathematician, so I have to use some maths. Okay, now the question number 2. Why whatever we were doing is this? Just, right? Because we can give an algorithm to compute this even in this setting. Okay? In 10 minutes, in 5 minutes. But I would like to tell first why whatever we were doing, like these sets and blah, comes into this. Okay? Let us do this, and all of you know this. So our sets are 1, 2, n. I'm going to make a matrix of dimension how much? P plus Q cross n. So V1, V2, Vn. So for each index I have a column. Okay? Each index I have. So for each index I have a column. And what is this? 1 square, 1 cube, 1 P plus Q minus 1, or yeah, 2, I think it is 1, 2 square, 2 q, 2 to the power P plus Q minus 1, 1, 3 square, blah, 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 1, n square. No, maybe I'm doing stupid. It's like 1, 2 power 1, 2 power 2, blah, blah, blah. I'm just writing van der Waals matrix. You remember, do you know van der Waals matrix? So this is what? So of dimension P plus Q cross n, this is all that I'm writing. So 1, n square, n to the power P plus Q minus 1. Okay, what is the property of this matrix? I tell you all columns of length at most P plus Q are linearly independent. Is this true?
Can you please repeat what property?
Look at this matrix. All columns of, look at any subset of columns of size less than equal to P plus Q. They all are linearly independent here. Right? Because you can take all this, you can find some small subdeterminant whose dimension, right? And if you choose anything which is larger than P plus Q, is it linearly dependent or independent here? What about P plus Q plus 1? Dependent or independent? For P plus Q plus 1 columns, my rows, number of rows in my matrix is P plus Q. Row rank of a matrix is equal to column rank of a matrix. So if I made explicitly that number of rows in my matrix is P plus Q, there is no way I can have P plus Q plus 1 columns which are linearly independent. Right? Now, a set of size at most this is at most P plus Q is linearly independent here. Now, whatever we were doing for sets can be translated into this language. Agreed or not agreed? Right? So whatever we were doing for sets, I can think of this problem by coming up with a particular matrix. What is that particular matrix? I make a van der Waals matrix of dimension P plus Q cross n. That's it. Right? Now any sets of size at most P plus Q is independent here. Anything larger is dependent here. So look at any Q, if it is disjoint, it is subspace. All that you need is disjoint. Right? That's it. So this is how I can reduce my problem in the beginning to this. Now how do we solve this problem? Good question, right? Okay.
Do you mean the problem to find the f?
I give you f hat, you gave me this matrix, you give me this matrix, you give me this f. I need to give you f hat. Now we need to make an algorithm for this. Agreed? And if we know how to do this faster, we know how to do this for sets also, because this is much more abstract. Sets versus subspace looks more general, right? Okay. So whole purpose is to do this, okay? How will we do this?
You mentioned Gaussian elimination.
Mentioned what?
Gaussian elimination.
Yes.
I see.
Think. This is a good time to take 5 minutes break.
Okay.
Or I need 15 minutes to finish this algorithm. All I need is 15 minutes. It will be slightly faster, but at least you will see how these things are used and done. Algorithm is trivial. Why it's correct takes a bit more time. Okay? But not much. If you know what determinants are, that's it. All I need is, I have got rid of matroids, I have got rid of everything, I have given you the most bare bone skeleton of what the theorems are and how you prove it. So, I'm going to make first simplification for the proof. First simplification. Okay? I will assume that this M is P plus Q. Sorry, M is M, N is P plus Q. Number of rows in your matrix is bounded by P plus Q. Okay? If you had given me any matrix and you were asking this problem, I can actually make this matrix of rows P plus Q. It is not easy, it is not simple, but you can do it. So take that as a fact. That is much simpler thing than what I want to tell you. Okay, now tell me, if this matrix has dimension P plus Q, which just means that when will you say a column of size P plus Q are linearly independent? If I give you column here, P plus Q columns here, when are they linearly independent? When, look, the rank of this matrix is P plus Q, or the number of rows in this matrix is P plus Q. I gave you some P plus Q columns and I want to say that these columns are linearly independent. When? Exactly. So when you take the corresponding determinant of these columns, the determinant of corresponding matrices should be non-zero. Agreed? So this is our starting point and this is the ending point of our algorithm. Okay? Now we follow our nice slides. Okay, some notation for you guys. Okay? By determinant of M, I will denote like this. And if you have a matrix M cross N matrix and I subset of M, J subset of M, Mij will denote matrix restricted to rows indexed by I and columns indexed by J. If I put star, means all rows but columns indexed by J. If I put star, all columns, just some notation, not too much. Okay. How did you people find determinant in the school? Say, you fixed a row and expand along the columns, right? No? This is the way you did. So suppose I fixed this row. What it is? You first fix this A41, delete this, then you did this, you deleted this, you did something, some computation here, here, right? And basically determinant of this matrix was sum of this plus minus this plus minus this as you went over this indices I and J. Agreed? This is how we used to find determinants in the school, 3 cross 3 matrix, 4 cross 4. Okay? Now this was in school, now we have graduated. So we will do more fancier stuff. Okay? This is called generalized Laplacian expansion. What I would like to tell you, if you remember from your school, that what did we do? What did we do here? We said A41 into determinant of this. But what is the determinant of this single matrix? Look at this A41, this A41. What is the determinant of that? A41. Right? So determinant of single matrix, like one entry matrix is itself. Okay, that's all. Not a big deal. Okay? So now I have this A, and now I fix some set of columns here, J. And now I want to find a determinant with respect to not one column, but with respect to fixed set of columns. So what you do is that, how do you do this? Now to find, you can also find, so what you do now is that you go over all rows of your matrix of size how much? Iterate over all I subset of your rows such that the cardinality of I is equal to cardinality of J, and basically this is what you do. You sum over all this, you have found some matrix, you find the determinant of that, and you find the determinant of the complement. Like if I have a square matrix, I fix some columns, right? I fix some columns. For example, I fix this column. If I find two subsets here, like I fix two rows here. So I got this entry, this entry, this entry, right? I forget this column, I forget this row, forget this row, forget this column. I will get two square matrices, right? One small one big one, right? So basically you can write determinant over, you fix some columns, you iterate over all rows of the same size, you take the determinant of the smaller matrix and take the determinant of the complement. This is what he's trying to tell you. I subset of n, I mod I equal to j, and determinant of A mod I comma mod j, and the complement of this guy. So this is a generalized formula for finding determinant. You should know that. This is very nice formula, and it comes in handy proving many, many things. So whatever we were doing for one, now we can fix a subset of columns and iterate over all subsets and make it small. And the proof is not very hard. You can just prove it whatever the way we were proving in this school. And you have some factor. What is this? -1 summation I plus. So look at the indices of your columns, indices of your rows, sum those entries. That's it. That is your error factor. But for us, let's not worry about this. This is what our determinant is. What is that? I go over all subsets, and we basically take the determinant of this, take the determinant of the other thing. Now, why am I interested in this? Okay, that's a good question. Why am I suddenly becomes interested in? You people notice that if I have a p-sized column here, why am I interested in this is that if I have a p-sized column here, I have a q-sized column from the future, and they are linearly independent if this determinant is non-zero. Agreed? Okay? All I am trying to tell is that I'm trying to think of determinant as a kind of big vector multiplication here. What I mean by big vector multiplication? Okay. What is this sums up to? If I remember correctly, suppose I have a vector a1, a2, al, b1, b2, bl. Suppose I define their coordinate by product a1, b1, a2, b2, al, bl, and sum them up, right? Summation ai, bi. I define some operation on two vectors. Then I can think of determinant as some big vector, something, and some other big vector, and they are summed over. Of course, I'm forgetting this -1 blah blah. For now, let's not worry about them. They are not important for our computation. Okay? So basically what I'm trying to do, what is this vector a1 to al is? What is this vector a1 to al is? Basically, it tells us that, okay, these are my determinants. Now, future, I can think of this vector b1 to bl, and current which I have in my hand, I think of a1 to al. Now, what is this happening? Okay, what I'm trying to achieve, let's try to understand picturesquely. So, I want to think whatever I have, right? So suppose I don't know the future, and I'm trying to expand along the p columns which I have. I know the future is q, right? So I'm trying to expand along my p columns. So basically I know the first vector, right? So basically what I'm trying to think, I have a vector space where I have a meaning of subspaces of dimension p. I'm trying to create another vector space where my p size subspaces are really vectors. You see what I'm saying? I'm trying to imagine a p size subspace at some vector in some other vector space. This is my whole goal. And how do I try to achieve this? I try to achieve this by going to some larger vector space of larger dimension where I can think of subspace as vectors. Then if I can think of subspaces as vectors, then I can think of notion of linear independence among them, right? So I will go to that space, I'll say, oh, compute your linearly independent basis here, come back, keep those subspaces, and you're happy. So that is the whole goal, okay? So I'm trying to make a vector space, big vector space, where each subspace of dimension P is a vector there. Okay, that is my goal, right? So maths allows you to construct these kind of objects. For example, if you take the cross product, like symmetric product, tensor product, ulterior, exterior, these are the ways to create these kind of subspaces. So all what we'll try to do is that I have this matrix means I have a vector space. Each column is my subspace. I want to create a big vector space where each of these subspaces are my vectors. That is my goal. How do I create it? It tells me. So if people have known a little bit of algebraic geometry, given a P columns, these coordinates are called Grassmannian. I don't know much. Please do not ask me. I do not know much about, okay? Or they also called Plucker coordinates. So my algorithm is very simple. In a minute I will tell you. So see, for example, if I were to expand along this, since I don't have time, I'm trying to give you as, see, I actually have made all this. I didn't do it. One of my students, she wrote a program to do it. I didn't know all this, to be very honest with you. I'm not even going to this. Okay, so this is my matrix, and here is my columns corresponding to some set Si. So this is my matrix whose number of rows is P plus Q. Now I have some set Si, and look at the call set Z. I have these columns corresponding to this. And this is my future which is going to come, and I know that together the determinant is non-zero. Because of this, they represent a subspace of dimension P plus Q. So what is the determinant AM star Z union Y? I want to compute the determinant of this matrix. This is equal to, not equal to 0. And let's expand along this set of columns. So what it will be? I subset of P plus Q, mod I equal to P, determinant of this matrix into determinant of the complement. This is what. And I do not care about this minus 1 blah. This is how I will write determinant. Now, for example, this could be this, then you determinant of this into this, and things like that. Okay? Now what I do, so given this set of columns, this is my big vector. What is my big vector? Well, at each entry, I basically, look, what do I have here? I have a p-sized column. I go through all p-sized, like p-sized row of this P plus Q. I get a matrix of dimension P cross P. Here, this is a matrix of dimension P cross P because I'm fixing these columns. I'm going over each P rows. This is a small submatrix of dimension P cross P. What I do is that I compute its determinant and keep it here. So given a p-sized, so what is this vector? This is my algorithm. We will be done in a minute now. So I have a p-sized column you gave me. What I do? I go over all p-sized subset of column. For each, I will get small submatrix. I'll get small submatrix, small submatrix. I compute its determinant and write it down as a vector. What is the size of this Vz? How many coordinates are there?
Please say it again. You asked a question.
No, I said, given this p-size columns, here, p-size column, I'm going to write a vector associated to this. And what is this vector? I say, okay, you fix some p rows from here. Now, columns are fixed. Each p rows gives you a p cross p matrix, right? Each column, each p rows gives you a p cross p matrix. It has a determinant, right? Because otherwise it is not defined. So what I do, I keep a big vector where for each p rows, I compute its determinant and keep it this. Choose p. So the number of entries in these columns, like number of this big vector. So given a p size subspace, I have made a big vector of dimension how much? P plus q, choose p. All subsets of size p plus q. So you iterate over this. So what is my algorithm? Very simple. You give me your sets, I compute this vector. So like you have S1 to ST. For VS1, I computed this vector. VSI, VST. How much time does it take to compute these vectors? If you notice, it is t into, let's write down this running time, right? To compute this vector. How much it will take? It is going to take to compute this t, p plus q choose p times p power omega, where p power omega is the time to compute a determinant of p cross p submatrix. This is running time to compute this. This is all that we took to compute all these vectors. Okay. Now we are done. Algorithm wise. Okay? Okay, so these are my vectors. What is the dimension of these vectors? P plus q dimensional vectors. Okay? I think of, so what is the basis of this? I have p plus q dimensional vectors. I want to find a basis for these vectors. What will be the basis of these vectors? I have t vectors. I want to find set of linearly independent vectors in these t vectors. How many of them will be there? What is the look, so think of this way, that if I write down as a matrix, it's a p plus, so this is going to be t cross p plus q choose p matrix. Think of this as a matrix, then number of rows is t based on number of objects, and the number of columns is p plus q choose p. So what is, and I want to find set of vectors which are linearly independent. Now since the coordinate is bounded by p plus q choose p, it is at most p plus q choose p. I'm only embedding this into a field. So if I had an object if my matrix was over a field F, where I have embedded these vectors. Think of a minute. I have actually embedded these guys in this. This is a space where I have embedded them. That's all. Now it means the basis of this space is p plus q choose p. That's it. Okay. And how much time will it take to find this? Write down them as a matrix. You can do it much faster. Okay. So what you do, you find this basis. They all correspond to some corresponding SIs. Keep them. That is your object which you are looking for. This is an algorithm. Why it is correct, we have to worry in a minute. But this is your algorithm. Given these SIs, I compute these big vectors, compute a basis in this. Corresponding to this basis, I take the corresponding sets and keep it with myself. That's it. Now why they're correct, I will show you some slides. It's not hard, but right? Okay. La la la. Okay. So suppose this is my basis. I have removed all the guys. What is the meaning of the basis? It means each of my vectors can be written linearly independent, like as a linear combination of these vectors, which means that each, yes, Vz can be written as this. Now it means each entry can be written as some, this is basically a linear combination of these guys, some lambda I this. Okay, right? So basically I can think of at each coordinate is linear combination of each of these guys. This is all that I'm trying to tell here. They're coordinate by linearly. Okay. Now I have to prove that whatever I have kept, what I know, determinant of A I Z is equal to lambda 1 times determinant of this, lambda t times determinant of this. This is nothing. I have just, so each entry is this. What is Vzi? This entry is exactly equal to this. By definition, I haven't done anything very brazen. What you do is basically, so look, I started with this. Now what is this determinant of AIZ? Is linear combination of whatever we have written in our subspaces. So let's substitute this with these vectors. Okay, so I think you people are a bit confused. I had these vectors, I computed its basis. It means, what is the meaning of this, that I computed its basis? It means that each Vz can be written as blah with respect to this. What I'm trying to say is that, look, if you throw away some set, then there's some set in U whose intersection with your Z is non-empty, and if you look at the determinant, it is non-zero. That's all that I need to show. There is S prime in blah blah blah, we have to show. Okay, so what I say, okay, so we started with this vector Vz, which is lambda 1 times my base, lambda 1 times this basis, lambda blah this basis. Now, what is this? This basically means that if you fix a coordinate, each coordinate of Vz can be written as a linear combination of the corresponding coordinates in my basis. Okay? Okay, which means that Vzi is equal to this, but by definition Vzi is nothing but this determinant. I just substitute there. Now, this is my formula. What I know, determinant of am star z union some future y is non-zero. This we know. I have to replace this z with someone which I have kept in my, in my solution. What I do to prove this, I said, okay, we have correctly kept it, so let's replace this determinant of aij with this number. I did this. Now what I do, I flip this summation. I mean, this is what I say, this is just some stupid mathematical summation. You flip this, so you go over I equal to 1 to r, summation I blah, determinant of a, I, ti, and whatever is the rest. And what you can show is that this object is nothing but determinant of your whatever vector you have kept with y. This is all that it is. You can write it like this. So basically you can write am star z union y is summation over I equal to 1 to r, determinant am star t1 union y. Okay? This is, so basically what I'm saying, and if you think of them as vector, it's just basically adding them up. So all we are able to do is that this non-zero entry is summation I equal to 1 to r, and ti's are the sets which we have kept, is summation of I equal to 1 to r. There's something is here, determinant am star t1 union y. Now if this is non-zero, what is the meaning of this? This is also, someone should be non-zero here. This summation cannot be 0 if this is non-zero. It will just mean that determinant of ti union y is non-zero for some ti in our family, and we are happy. That's all that it's trying to do. Okay? It's just a bit of, I mean, if you look at the book or something, proofs are much more cleaner than what I'm able to tell you now. And that's it. For at least one ti, this is going to be non-zero. And for such ti, y intersection ti is phi. Easily checked, all terms that survive have this property actually. And y union ti is in J, since non-zero determinant implies linearly independent columns. This is it. So if you think of them vectors, like basically this is what I said. What happened is very simple. You took this tuple, thought of them as a vector in this space, you found the basis for this and say, hey, now any determinant is a linear combination of these guys. So at least if this is non-zero, then with one of these guys must be 0, otherwise everything will sum up to 0. This is it. I mean, this is something which we do all the time. So once I tell you how to construct these vectors, how to find this, you can make your own proof why this is correct. So things to remember, you gave me this subspace, okay, this pi. I computed this long vector by going over all p cross p determinant, submatrix, and write down this determinant. This is my vectors. I computed a basis in this, and corresponding to this basis, I kept the corresponding sets, and we are done. Okay? And computing T basically, and compute a column. If you do this, compute a column basis, P plus Q choose row, T columns, it requires this much determinants. So basically, this much running time you need to compute this. Okay, this is to compute this big matrix, and there is a way, if the matrix dimensions are different, then this is a big one, and on the smaller you do omega minus 1. So this is a well-known method to compute, like do a smart Gaussian elimination. So this much running time of your algorithm, and this is field operation over f. Now for us this is great, because for kernel algorithm this is all p plus q choose q, everything is polynomial, things are fine and nice. And where it has been used more, this matrix approach to compute fast algorithm for determinant, like over tree width, like if you can do dynamic programming over graphs of bounded tree width using this matrix, thinking of them as what is called graphic matroid. This has been used in kernelization for odd cycle transversal, above guarantee vertex cover, and many other such problems where you use this matrix as a gamoid, I mean, as a representative set. So different matrices have a different correspondence, and you use this different correspondence to obtain many, many new algorithms. I think for one day, this is quite a lot. Okay, thank you. I'm done.